stabilized case. So in that case, the helium atoms have to bind, right? It cannot go out of the system. So rather I have generalized the question here. Leave helium dimer, take any diatomic molecule in the laser. What would happen to it? So you actually have three kinds of possibilities. Now you don't have a single Coulombic potential, right? Instead of that, you have that smeared kind of double well thing, which I showed you. Sorry. Yeah, this is what you have. So you have the same feature at two positions and separated by a particular distance. So what could happen is one could overlap, one could come on top of the other. Like when the bond distance is exactly equal to the quiver distance, what would happen is something like this. You will have something which looks like a triatomic molecule, or you could call it HHH, helium dimer in fact. Or rather HHEH should be a better way of putting it. But it's just a symbolic representation. The electrons actually see such a kind of potential. And the other option is when you have a distance of 20 atomic units, which is so then you have two separated units. And then you have another case in which the distance is I don't know how much distance. You could also have a potential possibility like this in which it looks like a tetraatom. Now, here just from the nature of the potential, you can see that you can create new kinds of chemistry for helium dimer. So, what we did next was, now once you have two helium atoms, and then you have a laser in the z direction, right? The direction in which both the helium atoms are. Now, the helium dimer is also free to rotate with respect to the laser polarization axis, and the rotation, it's no longer symmetric, right? The rotations are no longer symmetric because there is an electric field, a one-dimensional oscillating electric field in a particular direction. So the rotations are no longer symmetric. So what we did was we actually changed the angle with respect. If this is the laser direction, we changed the angle of helium around the laser, and we also varied the bond distance of helium. And we also changed this particular value called alpha 0. So after optimizing all these parameters, you remember in the first slide what I had shown you was they are very weakly bound, you had a very extended van der Waals molecule. So when the laser parameters got absolutely optimized, not absolutely optimized, optimized to a certain sense, to put a very deep well was there. And the bond energy was something about 12 eV. From 10 to the power of -7, from 0 to 12 electron volt. And you also had a bond distance of say 3.5 to 7 angstrom was the bond distance of this bond species which we found. So the idea is you can actually create new bonds using a laser, which stabilizes the whole system. So essentially, if you can create new bonds, that means you can do new kits. Now, we again try to look at how this particular bound state looks like.
How fast does the bonds decay?
Pardon?
How fast does the decay take place?
The decay takes place.
Yeah.
There is no decay in this particular case.
No, once you remove the laser.
Once I remove the laser. Now, this is a question which we are currently studying. How should you switch off the laser so that the state which you have created lives for a certain amount of time so that you can do new things with it? Or can you change the intensity and frequency of the laser? Because, see, this stabilization phenomenon which I talked about is not only a high frequency stabilization. Even in the case of low frequencies, this is actually going to happen because this parameter alpha 0 is epsilon 0 by omega square. So even at low frequencies, it has been reported in the literature that such kind of stabilization could happen. I have not looked at it as yet, but the next part of it, what we are going to do is actually how do you switch on and switch off the laser so that a new stable state exists for a finite amount of lifetime. And within that finite amount of lifetime, if you can do something new with it. So, but the initial part of the process is, yes, it forms a strong bond, the electrons remain stable in the system, they don't escape out of the system, so on and so on. But as long as the laser is on, it remains on. Now, this is a picture of the stable bound helium dimer. It looks a little bit strange, but see, it's a picture which corresponds to this particular. Sorry. It's a picture which corresponds to this particular potential. When you have a small part of the wave function here, then you have a double peak for the wave function here and a small peak here. So,
using this technique, then you can create heavy synthetic molecules which generally can't be created.
now, see this, whatever I talked to you about is within certain approximations. One thing is something called dipole approximation. So, the size of the molecule is much less than the wavelength of the laser. And yes, you could probably do reactions which are not possible. But for that, we would actually have to extend our calculations, include other effects, go beyond dipole approximation. Such kind of things have to be done. But that's also something which we would be working on. See, it's very similar to how would you switch on and switch off the laser. Like, and the other question to ask would be if you would apply the laser to a particular region of the molecule, what would happen? Now, this is the full row vibrational potential energy surface. I have given it in rectangular coordinates, but this is the well which it sees, where the strongly bound helium dimer would reside. Now, the one thing is, in the experiment I told you that the free field helium dimer had just a single vibrational constant. In this particular case, the depth of the well is so much that we had around 4,500 row vibrational constants. And the system actually rotates and moves within these 4,500 row vibrational constants very closely is spaced together. So the motion is almost constant. It's completely driven by the laser. So that is what that is another. And yeah. So the next thing what we thought about
The
is
shape of the potential would depend on the laser field.
it would depend on the symmetry of the laser. In this particular case, we have taken a laser which has an electric field polarization along the z direction. Yeah, that's one thing which I should also mention. You have an evidence for alignment. In fact, we found the maximum well depth when the molecule was completely aligned in the direction of the laser. So it's a different way of looking at. There's a lot of work on molecular alignment in lasers, and in those cases, how they look at it is you have a coupling between the row vibrational states of the system, and the interaction is a dipole interaction. Now here the potential is completely different. In fact, the laser interaction has been already built into the system. Still, it shows that there can be an alignment in the direction.
My question is this: you have the attractive part of the potential.
Yeah.
And
The
the attractive part of the potential basically at very long distance will be dominated by long range interactions. So here, would that
Here,
change as a result of the laser field?
Now here, actually, it would not. How would you quantify long range interactions? Is the question. Now, one way of looking at, in the case of free field, one way of looking at long range interactions is dispersion.
Yes.
Now, here, I would say that dispersion is not important. Now, the way I look at it is like this. Dispersion is something which relates to correlation energy.
Yeah.
Now, the laser atom interaction is a single particle interaction. And when you have a single particle interaction, generally correlation is not very important. And the other thing is you have a very spread out potential. You don't have a you have a very spread out potential, still the electronic repulsion also is not very large. There is a balance between a lot of things. The smearing of the potential, but a clear answer would be no, because the laser matter interaction is about the single particle. So the next thing what we did, so you have things like bonding, alignment, everything comes out of this particular picture. Now the next thing what you have is we decided to change the quiver distance for the same helium dimer. So what is plotted here is the distance between the two helium atoms and then I keep changing alpha 0. And all these are the ground states. All of these are ground states for a particular value of alpha 0. Say this is for a quiver distance of 1, 2, 3, so on and so forth. Now what is interesting here is this double well development in this particular case. Now for the time being, I think you should ignore this particular sentence. You should also remember that the depth of the well was such that there were a lot of bound vibrational states. Quite a lot of bound vibrational states. Now, if you would consider something like helium sulfur, we looked at also, we had taken sulfur atom and helium atom, so we also looked at helium sulfur. Now, this is not something we have just taken just like that. There is also a physical significance to it. Although the physical significance I came to know after doing this particular calculation. You do find helium sulfur kind of systems in very high astronomical fields in the galaxy itself. There have been measurements of it, so on and so forth. So it also makes physical sense to look at helium sulfur in a very high intensity, high frequency. Now, this kind of a double well develops for the ground state of helium sulfur. Yeah.
What kind of information you get from that?
The double well.
No, when you see from.
See, you have spectroscopic measurements. Now, it generally would not include the effect of a field or anything of that sort. But it was a very loose statement which I made, but you have such kind of things in the galaxies, is what I say. Now, the particular effect that I am looking at is this double well, right? Now, chemically, what would you call them? These are actually isomers. For two different, for the same chemical formula, you have actually two different bond lengths. Now, helium sulfur here is a molecule with a permanent dipole moment. Now, you could have vibrational states occupying these two wells, which are regenerate. Not in this particular case, but in probably some excited state, you would see that the vibrational levels are very closely spaced. In such a kind of case, you would have, here the dipole of the system is, there is a change in dipole moment as you keep changing on. Now you have an oscillating dipole moment when the system oscillates from one well to the other. So an oscillating dipole moment is what? Is another localized line, right? So the thing is if you would take such kind of molecules with permanent dipole moment, stabilized in the laser, you can keep changing the laser parameters such that such a kind of double well develops. And you would know this example of ammonia molecule, right? Ammonia has a permanent dipole moment. Now, if you consider the umbrella inversion of ammonia, you have a double well state, and you have two degenerate states, right? And then you have an oscillating dipole. So, similar to this particular mechanism, you could also have such a kind of mechanism here, and a localized light pulse would be produced for helium and sulfur molecule or helium hydride, so on and so forth in a laser, continuous wave laser, an extra light pulse. So that's another effect which we will be looking at, which is currently on. Now, just to give you a picture of how the electron densities look like, in fact, you'll have to break it up and look at it clearly to see that, you had sulfur atom which looks like oxygen molecule, which could be approximated to be oxygen molecule. You have helium which could be approximated to be H2 molecule. So naturally what you would ask is, okay, can we have something similar to OH, OH or OH dot dot O and OH and simple chemical. Now if you can look at these pictures and say that they look similar to that, then it's good. But these are the electron densities of the two isomers which you had in those double bonds. There is clearly a change in dipole moment, and thus we do have chemistry in the laser. Now, to summarize the whole talk, we put up three questions. One is, what is the physical picture of a very intense laser and an atom together? And then we looked at something called stabilization. We tried to explain something called stabilization. We have a small picture of how an atom would look like in the presence of a high intensity, strong laser. And then finally, we looked at new bonding effects in a laser. And thus we do have new chemistry and bonding in a laser. That is the whole message of today's talk. And I would like to acknowledge Professor Nanval Moisiev. I had done this work at his research group, and Curie Club for having given me this opportunity to speak here. This, to have a crowd here after 9 o'clock in the night, this was something which Rajaraman also told me, that he was inspired by it, so am I. So probably that's the end of the talk. And I would actually like to finish off by saying that very recently there were actually experiments carried out on helium atom. So the experiment, I'll just give you schematics of the experiment. What they had was a beam of helium atoms, and then they had a laser, which was a continuous wave laser, and they had a detector here. So initially, for a particular value of intensity and frequency of the laser, they could measure a momentum distribution of helium atoms on the detector. So next what they did was, they increased the electric field strength and the frequency of the laser of continuous wave. So what they saw was the momentum distribution of the ionized helium atoms reaching the detector decreased. Now the question is, where did those helium atoms go? And this particular experiment, both the papers actually attributed it to the kind of stabilization that we talked about. Then these were helium metastable states which they had to do. Because helium as such would be difficult to accelerate.